Hey guys, welcome back to a new video. In this session, we'll be tackling the concept of momentum, and in particular, inelastic collisions. As always, we'll be learning about this concept by looking at applications, meaning solving exercises step by step. The timestamp of each exercise can be found in the comment section below, where you can also ask any question you might have. Alternatively, you can also join our community of students by visiting our Discord server. The link is in the description below. So let's talk about momentum. We all know the formula for momentum, which says that P, the momentum of an object, is equal to the product of its mass m and its velocity v. And in this sense, the momentum of an object is simply its velocity weighted by its mass. And in this sense, it's a more fundamental physical quantity, since moving objects all around us always have a mass to them. That's why momentum is oftentimes preferred. Even Newton was aware of this, because he never wrote his second law, F is equal to m times a, in function of this a, the acceleration of a moving object. Instead, Newton wrote his second law as a function of momentum. Since we know that acceleration is simply the time derivative of the velocity, then we can put this m inside of the derivative, if it is constant, and then we see that we simply have the derivative of the momentum with respect to time. And this simplifies Newton's second law as simply saying that F is equal to the change in momentum. Therefore, if you want to change the momentum of an object, you need to apply a force. There is, of course, another very important reason why we oftentimes use momentum, namely that there is momentum conservation. Now, what does this actually mean? Let's say that we have a system that consists of multiple moving objects. If we then make the sum over all of the momenta of these objects, then the total vector representing the total momentum of all of these objects will remain unchanged however this system evolves in time, as long as there are no external forces. Therefore, we can say that the sum of all of the individual momenta before we let the system evolve will be equal to the sum of momenta after we have evolved the system. And in this sense, that the total momentum of a system is conserved throughout time. And this is a very fundamental law of physics. And as with any concept in physics, there are of course some conventions attached to it. So before we continue, let's first look at some sign conventions. In this video, we will consider one-dimensional systems, meaning that an object can go in two directions only. Let's say that we have an object with a mass of 3 kilograms, and we say that it moves in the right direction with a velocity of 3 meters per second. Then we can calculate the momentum of this object as being 9 kilograms meter per second. And this will be a positive quantity, so now we explicitly put a plus sign in front of it. If, however, this same object moves to the left with a velocity of 2 meters per second, then we say that the momentum is equal to minus 6 kilogram meter per second. Which basically boils down that in this video, by convention, objects moving to the right will have a positive momentum and objects moving to the left will have a negative momentum. One last thing before we go to the actual exercises. A brief word on collisions. And it is the distinction between two kinds of collisions. We have on the one hand inelastic collisions, where there is no rebound, and on the other hand we have elastic collisions, where there is in fact a rebound. Now you might ask, what is a rebound? Well, let's consider the case where there is a round object that is moving at a velocity towards a square object. We know intuitively that if these are two firm objects, then there will be a rebound, meaning that after the collision, the round object will be moving away from the square object. However, what exactly happens during this time of collision? Well, in an elastic collision, both objects will in a way squish or give way to each other. And they will be deformed for only a very brief moment in time. A perfect illustration of this in real life is, for example, a very slow-mo movie of a tennis racket hitting a tennis ball. At the moment of impact, both the racket and the ball deform. And since these two objects are deformed only briefly, when they pop back to their original form, this energy that was once stored to deform the object will now be used to catapult the round object back to where it came from. And the result is of course that the round object is now moving in the other direction. With this short explanation of these crucial concepts, you now have all of the tools in order to solve the exercises, which is what we'll be doing right now. In exercise 1, we are going to look at the collision between two objects. In the first scenario, we're going to consider two objects that are moving on a very slippery surface, meaning a surface without any friction to it. The first object has a mass of 1 kilogram, and so does the second object, so both objects have the same mass. Now the difference is that the first object is moving to the right with a velocity of 3 meters per second, whereas the second object has 0 velocity, meaning that it is just at rest. Given these conditions, our magnificent intuition says that there will be a collision in the near future. Both objects will hit each other, and the exercise now is to find the velocity of both objects after this collision. And this under the assumption that the collision will be 100% inelastic, meaning there will be no rebound, and I will get back to that once we need it in this exercise. The first step, of course, is to write down the givens that we have in this problem. We have v1, which is equal to the velocity of the first object. This is, of course, 3 meters per second. We have m1, which is the mass of the first object, which is 1 kilogram. We have v2, which is the initial velocity of the second object, which is 0 meters per second. And of course, we have m2, which is the mass of the second object, which is also 1 kilogram. So these are all the givens that we have. And since we are asked about the velocities of both objects after a collision, and because this is a video on momentum, we are of course going to use the conservation of momentum, meaning that the total momentum of the two objects taken together before the collision will have to be equal to the total momentum of these objects after the collision. This is exactly what conservation of momentum means. And in order to use this fundamental law of physics, we need of course to first calculate the total momentum before and after the collision. And in order to not make the notation too cumbersome, because we need to distinguish the quantities before and after the collision, I simply use a color coding. All of the quantities before the collision I write in blue, and all of the quantities after the collision I will write in red. So before the collision, we have that the total sum of our momenta, so the sum of py, is simply the sum of the momentum of the first object with the momentum of the second object. And since we know the formula for momentum, we can fill this in right away. We have m1 multiplied by v1 plus m2 multiplied by v2. And these are the initial quantities, which are of course given right here. So we can fill this in right away. m1 is 1 kilogram, v1 is 3 meters per second. And note here that since the object is moving to the right, we have a positive momentum, so a plus sign, plus m1 is also 1 kilogram, but v2 is 0 meters per second. And this comes out to be a total momentum of 3 kilogram times meters per second. And this is of course the unit of momentum. So we know that the total momentum before the collision is equal to 3 kilograms meter per second. Let's now look at the situation after a collision has taken place. We can again calculate the total momentum, which is simply the sum of all the momenta, and this of course will again be the sum of the individual momenta of both of these objects. So this simply becomes again m1 multiplied by v1, but since I'm writing v1 in red now, I explicitly mean the velocity of the first object after the collision, plus m2 multiplied by v2, the velocity of the second object after the collision. So what do we exactly know from these four quantities? Well, we know m1 and m2, which are the masses of both objects, and these remain unchanged. What we don't know is this v1 and v2, the velocity of both objects after the collision. However, at this point, we use the fact that we have a 100% inelastic collision, meaning that there is no rebound. And since there is no rebound, when these objects collide, they simply will have both the same velocity. Since there is no rebound of object 1 bouncing off of object 2, they will simply have the same velocity. So because of this, we can say that v1 after the collision is equal to v2 after the collision. And we can write this in our sum here. So we have m1 times v1 plus m2 times v1, because we've now written v2 simply as v1. And again, this is only because we have a 100% inelastic collision. This simply becomes v1 multiplied by m1 plus m2. And at this point, we use the fact that we have conservation of momentum, meaning that the total momentum before the collision, which we calculated to be 3 kilogram meters per second, will have to be equal to the total momentum after the collision. So this will have to be equal to 3 kilogram meters per second. And now we can rewrite this equation to find, of course, the variable that we were looking for, this v1. And since we have v1 is equal to v2, if we find v1, we also have v2. So rewriting this equality sign right here, we have that v1 multiplied by m1 plus m2 is equal to 3 kilogram meter per second. Or we can write it differently as v1 is equal to 3 divided by m1 plus m2 kilogram meter per second. Therefore, filling in the numbers, we have that v1 after the collision, which is equal to v2 after the collision, since they are both moving at the same velocity, is equal to 3 divided by 1 plus 1, 3 divided by 1 kilogram plus 1 kilogram, and let's not forget this unit that we had for momentum, kilogram meter per second. And of course, we see that these kilogram units, they cancel out, and we are left with meters per second, which is exactly what we need for a velocity. And this comes out to be 3 divided by 2 meters per second, or simply 1.5 meter per second. And this is our final result for both v1 and v2. So after the collision, both objects move at the same velocity, which is half the velocity of the initial object. So just for clarity, let's now sketch the situation after the collision. We have, of course, here our object 1, and we have adjacent to it our object 2, and they are both moving at the same velocity of 1.5 meters per second, which is exactly half of the velocity that our initial object had. And this is a very nice illustration of conservation of momentum, since we, before the collision, had 1 kilogram moving at 3 meters per second, and the other one being at rest, and after the collision, we had 2 kilograms, so double the mass, moving at 1.5 meters per second, or half the velocity. So where the mass increased with a factor of 2, the velocity decreased by a factor of 2. And this is exactly conservation of momentum. Let's now look at a second scenario that is a bit more involved. So we have scenario B. So we again have the same situation here. However, now the initial situation is that the second block is not at rest and is also not equal to 1 kilogram. In this second situation, we have a block of 2 kilograms that is moving in the opposite direction with a velocity equal to 2 meters per second. And again, the question is to find both velocities after the inevitable collision. Again, our givens are, of course, that v1, our initial velocity of object 1, is 3 meters per second. Its mass m1 is equal to 1 kilogram. Our second initial velocity is now minus 2 meters per second, since it is moving to the left. And its mass, m2, is equal to 2 kilograms. And again, to solve this, we are going to use conservation of momentum. And for this, we again need to calculate the total momentum before and after the collision. So before the collision, we of course have m1 times v1 plus m2 times v2, since there's only two objects involved in this situation. This can be now easily filled in. m1 is 1 kilogram, v1 is 3 meters per second, plus the mass of the second object is now 2 kilograms, and the velocity of the second object is minus 2 meters per second. Adding these up, we have 3 kilogram meter per second minus 4 kilogram meters per second, which results in a total momentum of minus 1 kilogram meter per second. And we see here a minus 1. This simply means that given these two objects together, the total momentum is to the left. And this can be seen because even though this object that is moving to the right has a larger velocity, it has a much lower mass. Let's now look at the situation after the inevitable collision of these two objects. We know, of course, that the total sum of momenta is equal to m1 times v1 after the collision plus m2 times v2 also after the collision. Now we of course already know that this sum will have to be equal to this minus 1 kilogram meter per second, since we have conservation of momentum. Filling this in, we have m1 still remains 1 kilogram, v1 we don't know, plus m2, which is 2 kilogram, multiplied by v2, which we also don't know. However, here again we use the fact that we have a 100% inelastic collision, meaning that after the collision, both objects will move at the same velocity. And this is because there is no rebound. So v1 and v2 after the collision will have to be equal to each other. So we can write this as follows. We have 1 plus 2 kilogram, which is factoring out this mass, multiplied by v1, which is equal to v2. And we know that due to conservation of momentum, this has to be equal to this one right here. So minus 1 kilogram meter per second. And now we have an equation that we can already solve. So we find that 3 kilogram times our unknown velocity is equal to minus 1 kilogram times meter per second. Or moving this 3 kilogram to the other side, we have that v1 is equal to minus 1 over 3 meters per second, where we already cancelled out the unit of mass kilogram. And this is our final result, which says that in our initial situation, that after this collision, both of the objects will be moving to the left with a very low velocity of minus 1/3 meter per second. And let's now go to the second and final exercise. And in this exercise, you find yourself running at a high velocity towards a cart, just something that has wheels on it and on which you can stand. And the idea is that you're running towards it and then jump right onto it. Now this cart is initially at rest, and the question of course is at which velocity you will continue rolling on this cart if your initial velocity and mass are known. Let's say that you weigh a healthy 70 kilograms and that the cart has a yet to be determined mass. Again, we clearly have a before and after situation here. The before situation is where this cart is at rest and you are moving at a velocity of, let's say, 3 meters per second. And then the after situation is where you have jumped on the cart and are now moving together with the cart at a to be determined velocity. And now to determine the velocity of yourself in the cart after you have jumped on it, we of course again invoke the conservation of momentum. And to do this, of course, we again need to determine the total momentum before and after the action has taken place. Before, we have that the total sum of individual momenta pi is equal to the following, again following the color coding that I am using here, before in blue and after in red. We have m1 multiplied by v1, which is the mass and the velocity of ourselves running towards the cart, plus the mass of the cart multiplied by the initial velocity of the cart, which we call v2. This can be simply filled in as being 70 kilograms multiplied by 3 meters per second plus capital M, to be determined, multiplied by 0 meters per second, because the cart is at rest. And this comes out to be a total momentum of the combined system of cart and yourself before the action has taken place to be 210 kilograms times meter squared. Now, because we have conservation of momentum, we have, of course, that after you have jumped onto the cart, the total momentum also has to be the same. So this becomes m1 times v1 plus capital M times v2. We know that this becomes m1, your own mass, times v1, the velocity that you have after you have jumped on the cart, plus capital M, the mass of the cart, multiplied by v2, the velocity of the cart after you have jumped on it. And we know, of course, already that this sum will have to be equal to 210. Filling this in, we have 70 kilograms times v1, the velocity to be determined, plus capital M multiplied by v2, also the velocity that needs to be determined. Of course, we have two variables here again, but we remind ourselves that after we have jumped on the cart, it would be preferable if the cart and ourselves have the same velocity. Otherwise, we would just be falling off. So v1 and v2 are simply the same. This means that we can write this as v, the velocity that we need to find. So it could be either v1 or v2, they're just the same, multiplied by 70 kilograms plus capital M. And since we know that this term right here has to be equal to 210, the total momentum before we jumped on the cart, we have ourselves a very nice equation. We have that 210 kilograms meters per second has to be equal to v1, the velocity of the cart and ourselves after we have jumped on, multiplied by 70 kilograms plus m. Or written this differently, we find that 210 divided by 70 plus capital M kilogram multiplied by kilogram meter per second. And we can cancel this kilogram right here, such that we of course only are left with the units of meter per second is equal to the velocity that we are looking for, the velocity that we have together with the cart. And at this point, we have a general formula that we can now simply use and plug in different values for the mass of the cart. Let's say, for example, that this cart is actually a skateboard and that the mass, capital M, is simply 0.5 kilograms. If we fill this in our equation, then we find that the final velocity that we have is equal to 2.97 meters per second. And let's remind ourselves that our initial velocity was 3 meters per second. So our velocity didn't decrease at all. Let's say that our mass of the cart is now equal to 10 kilograms, for example, a shopping cart. Then filling this in, we see that the final velocity is equal to 2.62 meters per second, or a decrease of almost 15%. Now, what if the cart is 100 kilograms? Well, then our final velocity will be 1.23 meters per second, or more than half the initial velocity. Let's now say that this cart was actually a car that was standing at rest, which is around 1000 kilograms. This means that if there is a car at rest and we would run very hard towards it and then jump on it, that the final velocity that the car will have is 0.2 meters per second. And this means that you probably also hurt yourself because your velocity goes from 3 meters per second all the way down to almost 0. And it is in this way that we can use conservation of momentum to calculate the final velocity of inelastic collisions. And this brings us to the end of this video. And if you made it all the way through the end, I am very proud of you. Leave a comment in the comment section below. If you enjoyed this video, give it a thumbs up. If you want to get notified by future releases, consider subscribing. And with that, I thank you for watching and I will see you in the next one. Bye.